I'd like to welcome you all to Retro Rabbit. Thank you for coming through again. And I'd mostly like to introduce Cillié Malan, who's one of our resident geniuses. And I think he'll get a little bit more into it, but you know, blockchain is a really prominent buzzword these days. And I think a lot of us talk about it and we don't know how it works. So everybody, a round of applause for Cillié, and he's going to teach us some things. Once again, quickly, if you look over there, there'll be some drinks. If you can't find anything, look in the bar fridges. Bathrooms are over there, and feel free to have any food. Take it away, Cillié.
All right. So, like Jade said, blockchain is a pretty big buzzword these days. And I have seen a lot of people talk about blockchain and that spend a lot of their time studying blockchain and cryptocurrencies and smart contracts and these things. And when they start to explain how it works, I can tell that they don't really grasp the nitty-gritties of how it works. Because with blockchain, the devil is in the details. There's a lot of small things that can be misleading and can give you an impression that a blockchain is something that it is not. So today I'm going to talk about blockchain. We're going to talk really about blockchain as blockchain, not really any of the ancillary stuff that's going on with blockchain. We're just going to talk about the technology. And the way that we're going to talk about it is we're going to look at a very minimal but very working blockchain solution or a blockchain application. And I will encourage you, those of you who have laptops, download the source code and follow along with me as we study it and we see very much to the details that a programmer does how blockchain works. So, before we go on, be sure you're on the Wi-Fi. It's going to be important because blockchain is a distributed, decentralized system, and in order for it to work as a blockchain, it needs to be able to communicate to other nodes. So you need to be on the Wi-Fi if you're going to be able to do that and if you're going to run the blockchain on your computer. And that's a point that I need to just stop and wake. And there's a lot of these kind of build your own blockchain things that I've seen in recent months. It seems to have exploded since I started preparing for this. I started preparing for this a few months ago, and since then it seems like every week there's a new article of how to build your own blockchain in Node.js. And the thing about those is it's usually just one article. And blockchain is not really something that you can cover in one article that takes 5 minutes to read. That's why we have 2 hours tonight. And hopefully we won't take an entire 2 hours, but we're gonna go through all the details. And the thing that people tend to leave out in these build your own blockchain things is that is unexpected. Does that mean the show is over? Everybody stay calm. I don't know what to do. When this fire alarm goes off, I'm going to use my ignorance to your advantage. That's better. I'm assuming that means that there is no fire. A funny story, I was in residence when I was studying at university, but this was not in South Africa, this was in Canada. I studied a semester there, and it would be in the winter, and over there if the fire alarm goes off, you have to evacuate. And the people in the building can't turn the fire alarm off. The fire brigade has to come and turn the fire alarm off. So as university goes, it was 1 o'clock in the morning, more than once, somebody would pull the fire alarm, and we would all be standing outside in the snow, waiting for the fire brigade to come and turn the fire alarm off. And that was fun. But, so, fortunately, we don't have to do that. So, as I was saying, we're going to be looking at how blockchain works by building it, and I hope that that would bring out a little bit more detail in your mind as you're trying to understand blockchain, so that if we want to go to more complicated blockchain things like looking at smart contracts in Ethereum, you would have kind of the groundwork of how the blockchain actually works at its core, to be able to understand how the technologies built on blockchain work. So this is what we're going to look at today. We're going to look at how does blockchain work. We're going to look at the cryptographic principles. We're going to look at the concept of validity. And we're going to look at proof of work. And we're going to look at how this all comes together into a working solution. Now, what we won't look at is anything to do with cryptocurrencies. Now, we're going to build a digital ledger like Bitcoin. What we're going to build is based loosely on the original Bitcoin paper. But we're not going to be talking about all the cryptocurrency blah-de-blah and the value of Bitcoin and how do you determine the value of something that doesn't exist and what will Bitcoin's value be next week. We're not going to be looking at altcoins and all these other things that they have these days. We're not going to be looking at other kinds of proof. We're going to be looking at proof of work. We're not going to be talking about proof of stake and all these other things because that also becomes really complicated. Proof of work really is a very fundamental thing on how the blockchain works. We're not going to be talking about smart contracts, as interesting as that is. That might be something we can look at a different time. But today we're going to look at kind of a bit more basic things. And we're pretty much not going to be looking at anything to do with blockchain that isn't a stock standard ledger. So the basics. Let me just ask this question. Who hasn't seen some sort of video explaining how blockchain works? 1 or 2 people. Well, congratulations. Hopefully you'll get a clean slate this time. So if you're a programmer, explaining blockchain to me is very simple, how the blockchain structure works. It works like Git. So how it works is you have these blocks. A block is something that you can't really see on the projector, but I will read out for you. A block, fire alarm. A block is something that has data. It has a hash, which is to say it's the digest of the data. And the idea behind the hash is if any of the data changes, the hash changes completely. And other than that, you cannot predict what a hash is. So if you cannot say, I want this data and it must hash to this value. That means if you have the hash and you have the data that hashes to that value, you cannot change the data without changing the hash. And you'll see in the next slide why that's important. So a block has some data, it has a hash, and this is the important part, it has a parent. Now the first block, the parent is null. The parent is 0, it doesn't exist. So there's nothing here. But for the first block and every block onward, there is a parent, and the parent is very simple. The information that the parent contains is the hash value of the parent block. So if you don't have this block and you have the hash, you don't have anything. You need the block. If you have the block, you can hash the block, and you can say, this block is the child block of this block. Now, the reason this is important is because the parent value is part of the hash. So if you change the parent value, the hash will change. So in other words, I cannot change this block, and this block still point to it. So once this block is created, pointing to this block cannot be changed, because this block points to the hash of this block. And that's why you get this. So let's say somebody does try and change this block. You've got a blockchain. Somebody hacks into the database, let's say, publishes to all the nodes an invalid block. And they change some stuff. Now the hash is going to change. Now the blockchain going this way will still point, because of the hashes, to each previous block. But the new block, which has the erroneous or malformed data, will have a new hash. So the existing blockchain will simply ignore this block. And that's how the blockchain is designed to work. So this is kind of how the blockchain even resolves competition. So this is one of the principles of what makes a blockchain work, is you've got multiple nodes all competing to calculate the next block, because there's a lot of value in the block, and we'll talk about that a bit later. But the reason why it doesn't matter if somebody publishes a malicious block or if somebody publishes the same block with different transactions is because the block that they publish will have a different hash. And this is where a key principle in the blockchain comes out. The way that you decide which blockchain is the right one is the blockchain that's the longest. And so the longest blockchain, whichever it is the one that's right. And so if somebody else changes, say, a block that's 6 blocks away from the end, it will become a new block. But this new blockchain is now 6 layers shorter than the other blockchain. So even if somebody were to get all the computing power that's needed to create a separate blockchain, for the Bitcoin blockchain, for example, there's absolutely no way they'd be able to recreate the entire blockchain. It's hundreds of thousands of blocks deep. But even if you were to change the past few blocks for the past hour or so, I mean, with the Bitcoin blockchain, for example, a block is created every 10 minutes. So you would have to, if you want to change a block that's 6 blocks deep, you'll have to recalculate 6 different blocks in order to overwrite the actual blockchain. And now this actually happened a few weeks ago. There was a double spend attack on Bitcoin Gold, and the way that they did it is somebody managed to get enough computing power to be more than the entire rest of the blockchain combined, and a bit more. But I think even then it shouldn't have been possible. And we'll come to that a bit later. But I just want you to understand that this is a core principle, is that the blocks are not changeable once they're created. And the whole network will accept whatever blockchain is the longest as the correct blockchain, because that would represent the blockchain that the most work went into. And that is another core principle of blockchain, is proof of work. Now there are other proofs that exist, like proof of stake and proof of space and all sorts of weird proofs. But proof of work was the original suggestion, and it's really pretty hard to get past how pragmatic and simple and effective proof of work is. Now, how proof of work works, we'll go into the super technical details hopefully soon. But how proof of work works basically is this. For every block, there is a hash. And very simply, in the case of the Bitcoin proof of work, they said the hash must be less than a certain amount. So typically a hash would be completely random, because that's what a hash is supposed to be. You're not supposed to be able to predict the next value of a hash based on the data, and so that's the same, or more or less the same thing as saying it's completely random. But if you change something small within the data, and it's called a nonce, the number used only once, if you change the data around a little bit, the hash changes completely. So that's how proof of work works. You keep changing this little number over and over again, and the hash keeps changing wildly. And when you get one that's under some certain really low value, you've got a block that basically proves that you have done statistically a certain large number of hashes to be able to figure out a nonce or a block that matches the certain very specific criteria. And the reason you can't get past that is because there's no way to predict what a hash is going to be. You cannot reverse engineer a hash. And so to give an example, for the Bitcoin blockchain, you would have to do, a single computer would have to take like 30 years or something of computing to be able to find the hash value, to be able to find the nonce that would have to kind of recreate a single block. So for the Bitcoin blockchain, it takes, and for all the other blockchains out there that use proof of work, it takes the distributed computing power of thousands of computers, and they're not even computers anymore, they're just dedicated hardware, calculating this hash value, keep changing the nonce, which is just one little value, that keeps changing the hash value, and it just keeps doing that over and over again till somebody finds the right one. And this brings us to the next part of the principle of the blockchain. The person who finds this magical value that makes the block hash go below a certain value, that person, that node, that computer, has the right to create the next block. And as soon as that block is found, it is signed by that that person or that computer that found that value, and it's published to the rest of the nodes. The rest of the nodes check the value, and they say, "Ah, yes, the solution to this problem is valid, and therefore we will accept it as the next block in the chain." And so that's kind of the fundamental principle. And really all that it boils down to is it takes time to create one of these. It takes time and resources to create a block. And that prevents fraud because there is an incentive to create a valid block. The incentive is in case like of Bitcoin, there's a block reward, but there's also transaction charges. And that's basically when you're dealing with a ledger, there's a small amount of money. Well, it's supposed to be small. It's very large because of the value of Bitcoin. There's an amount of money of Bitcoins that goes to the person who finds the block. So they have an incentive for working towards the block. And that's kind of all the nodes working together trying to find the block. And so, excuse me. Before we go on, is there any questions about how blockchain works? And so I just want to make sure that we understand kind of the basic idea behind blockchain before we go on. Any questions? Going once, going twice. All right. So this is the process. And I know it's completely illegible. So I'll talk about it. And I've got the next slides that zoom in a bit. So what I've got here is a diagram of the process of mining. That's what they call the work of trying to find the next block. So how it works is you've got kind of a way to communicate with other nodes, and this is what the top part represents. And we've got our process. We've got, in here we have a database of all the blocks that we know about, and we keep that around in storage. In memory, we keep a pool of transactions. Now, transactions is what we're going to work with. You've seen in these slides, I just keep saying stuff and more stuff and stuff, because it doesn't really matter what's inside the blocks. But in our case, we're going to be building a ledger, the same thing that Bitcoin was designed for, and really the hot thing that blockchains have been about up till now, before we had the thing of smart contracts and so on. So we're going to be building a ledger, and for a ledger you have transactions. And so whenever a new transaction needs to be made on a blockchain, all that happens is somebody publishes this transaction to all the nodes, broadcasts it to all the nodes, and the nodes, or node in our case, puts it in a pool of transactions that it keeps in memory. This pool of transactions gets applied to the block that we're trying to create. And so let's go through the process. So the first thing we do is the application starts, and we initialize the blockchain. And all that this entails is, you see that arrow is going up, is this node might be new to the blockchain group distributed computing system. And so what it's going to do is it's going to ask the rest of the nodes, give me the blockchain. And give me all the blocks that you know about. And they're going to send all the blocks, and we're going to fill up our database with the blocks that the other nodes know about. And we're going to basically just verify and build our own version of the blockchain. Then we're going to ask, what is the tallest block? And that's something I skipped over a bit. And that is, each block has a number in it that's called the height. Well, I called it the height. I think Bitcoin calls it something else. But basically, that you see this one is a 0 parent. This is the height 0 block. And then this one is height 1, height 2, height 3, and so on. And the tallest block is the block that is the newest one. So we ask, what's the tallest block? What's the block that's the furthest from from the first block? What's the block that's the furthest from the first block? And what's the block that doesn't have any blocks coming after it? We're going to make that our new parent block. So we're trying to find the next block, and we need to reference the parent block in our block. And so we want to know what the tallest block is. That's our new parent block, and that's all we need, and we start solving. And that's where the proof of work comes in. So we now have the problem that we need to solve, and we're going to do work, going through hashes, and just keep changing our nonce around until we find a solution. If we don't find a solution, we just work some more. And that's literally how it works. Just keep changing a number by 1 digit and hash again. And yes, question?
In this scenario, are you only hashing that single nonce? Is that all you're hashing, or do you hash that and block?
Programmer question, thanks. The question is what are we hashing? Are we hashing only the nonce, or are we hashing the entire block? That's a good question, because I changed it up from what blockchain does, with what Bitcoin does. Bitcoin hashes the entire block. So if you go onto like a blockchain explorer that shows the data of the blocks, you see all the hashes for the blocks are like these very regular values, which if you've seen hash values at all, and like open your Git repo and look at the history, you see the hash values are like random. But the blockchain hash values, they're very regular. The first like 20 numbers or something, not 20, but like large number of numbers at the front of the hash value are all zeros. And that's because they're supposed to be less than a certain value. Our blockchain solution is not going to do that, because the algorithm for calculating the hash is going to be too slow, because it's in Node.js. So, so I changed it up, and in our case, we're hashing only 32-bit value, and we'll get to that. In our case, we're not hashing just the nonce, but close. Something like that. Anyway, but it's the same principle. We're trying to find the solution to a problem. The problem can be verified by other nodes. And the problem is based on the hash of the block. Our blocks won't have pretty hashes. Okay. And now the question is, what if somebody else discovers a new block? Or what if a transaction gets added? If a transaction gets added, the block needs to change. And so whenever this happens, there's basically two things that can happen. Either a new block is discovered by someone else, and in the real world, this is extremely likely that somebody else is going to find that block. Somebody else is going to find the block, and they're going to broadcast it to the network, and we get the new block, we accept it as the highest block, and we start over. So a new block gets received, it goes in here, and we start over. What is the tallest block again? Oh, it's the new block. Now it's our parent. The hash has changed. We start over. Solve. Work. Same thing happens when a new transaction is received. When a new transaction is received, it goes into our pool, into our block, and our block the hash of our block changes. And you can't read it, but I say that the hash of our block keeps changing as new transactions are added. And when the hash of the transaction changes, oh my goodness, keyboard doesn't understand me. It also means we have a new problem and we start over. Now it might sound like work is going to waste, but it's not. Because we're trying to find something that's random. So if we change the problem, it doesn't change the fact that what we're trying to find is completely random. So if we keep changing the problem around, it's not going to decrease the likelihood of us finding the problem on any given try, which is why this kind of thing doesn't matter. So we can just keep hashing, and we just keep changing the thing that we're trying to hash, and it doesn't matter. Okay, and now let's say we find, yes, question.
What if the two nodes find a block at a similar time and both broadcast to the network? How is the network choose which block to follow?
Okay, so the question is, what happens if two nodes find a block at roughly the same time and it gets broadcast to the network? How does the network decide? And the answer is, the network, each node in the network can decide however they want. And the reason it doesn't matter which one they choose is because whichever person finds the next block, that block will now be one level deep and the other block will be discarded. So that's why when you see these websites and so on that take blockchain or Bitcoin as currency, they say you have to wait till your transaction is a few blocks deep before you mark it as verified, because it could be that block gets created and another block gets created at the same time, and half the network accepts one block, half the network accepts a different block, and then 10 minutes later a new block gets created, but the block gets created is by a node that didn't accept the block with your transaction. And that block is now no longer part of the tallest blockchain and then just gets ignored. In that case, you'll have to resubmit your transaction. Now, this is not, it is very unlikely that this happens, but it does happen. And that's a good question. And another question that actually, or when you start looking at the details of Bitcoin or of blockchain, another question is, what about this? Who decides what transactions go in the block? And that is, like we said earlier, the node that finds the solution creates the block. And the node that finds the solution can decide what transactions go in that block. Yes, question?
So on that node, if I'm understanding it correctly, so you have sort of this database of possible transactions that are published. So every person who goes and says, I want to transfer 5 Bitcoins to the person next to me, I want to have this transaction made. And people who try to generate the hash that's lower than a certain value in Bitcoin's case, or whatever the criteria is, can pick a random set of those transactions. Because as I understand it, there are a fixed number of transactions per block.
Exactly.
So you pick a random nonce and a random set of transactions and try to hash that to something that's valid.
So the question that he asked is, so the nodes just choose a random set of transactions when they create a block, because there's a limited amount of transactions that can go to a block. And the answer to that question in Bitcoin's case is, the nodes are incentivized to choosing as much transactions as possible, because there's a transaction fee that goes on every transaction. And so the way that that works, and we'll get to it, is the money that goes out of one account and the money that goes into the other account aren't equal. So there's slightly more money going out of the account than there's going into the other account. And the amount that's the difference is the transaction charge. And that amount gets applied to whoever finds the block. So they're incentivized to put as many high value possible transactions into the block, because then if they find the block solution, they get to keep that transaction charge. But there are blocks on the Bitcoin blockchain that don't have any transactions in them, because that's completely legitimate. to create blocks without any transactions in them, because there is a disproportionately large block reward in Bitcoin's case, because Bitcoin has become so valuable. So it's, what's it now? It's like 12.5 Bitcoins if you find a block, which is like millions. And so if you don't include any transactions, you can have about 2,000 transactions, I think, in a block. And you can make about like $10,000, maybe $100,000 on the transaction charge, but you can make many millions on the block reward. So some people maybe think that it's quicker if you just leave out all the transactions. Technically, it probably doesn't make any difference. But it does show that even though nodes aren't exactly incentivized to keep transactions or not, they are keeping the transactions anyway. But that means, yes, the node that finds the reward gets to make the block and gets to choose where the blockchain is going. Yes?
The priority of the transactions, how does that come into account? Does that play any role?
So question there is, what's the priority of the transactions? And again, the node gets to decide what the priority of the transactions is, but the rules in the Bitcoin blockchain, for example, is the highest transaction charge goes in first. So if there is more transactions than there is space in a block, then the highest value transactions will get put in first by the blocks, or by the miners. Okay. Any other questions? Cool. So when the block is found, it's very simple. The block gets signed. This is in our case. In the Bitcoin, I think the block gets signed first. But in our case, the block gets signed, and it gets published to other nodes, and the process just repeats. It just goes back to here. Oh, we received a new block. And we'll see in the code, we actually just call the same function. All right. So let's dig into the code. And yes, question. How do you read from a blockchain? You connect to the other nodes. So in the Bitcoin blockchain, they have some distributed protocol. You connect to that protocol. You're a node in the blockchain, although you may not be a miner. You may not be mining you may not be mining for the next Bitcoin, but you're still connected to the other nodes, and then you can get all the information, you can send transactions, you can receive all the new transactions, and so on. So that's basically how you communicate with a blockchain. Some people have APIs and stuff, and that's generally what you do, is you just connect via intermediary. But the most straightforward way is you can just connect. So what I would like you to do is, if you have a laptop, is you can clone this repo, and we'll look at the source. I'll put it on Slack. Who does not have access to the Rabbiteer Slack? Okay, a few people. You're going to have to write that down, because I'm going to just put it on the Rabbiteer Slack. Can I automatically get on Rabbiteer Slack from the website?
Yeah, so if you go to rabbiteer.io, at the bottom there is a Slack link, and you can join the Slack from there.
Yeah, so if you're not on Slack, you can just go to rabbiteer.io and join it. Or somebody will just help you. Anyway, this is very simple. HTTPS github.com/Cillié Malan. It's my name. It was supposed to be Retro Rabbit, but I had a bit of a tough week. And I didn't have time. So this is on my name /BYOB for bring your own blockchain.git. And you can just clone that. So yeah, yes, question? 2 L's. CILLIE. So I just, at this point, I have to apologize. This is the end of my slides. Because I got struck with a plague this week, and I was sick from like Monday. And so I was a bit behind. So from here on, we're just going to look at Visual Studio Code.
I wrote it over there. Cillié couldn't do this, and you have to move it because he thought he was going to have an appendix surgery.
Note to self. People tend to react rather severely when you say that. Maybe wait till after the doctor. Okay, so please try and clone the repo. If you have any problems, I'm going to stand here and you can ask me and I will give you advice. I'll just give it like 1 or 2 minutes for you to say git clone. The other prerequisite is you're going to have the newest version of Node. Derek was kind enough earlier to test and say you need 6.10 or something, but seeing as that, what? It doesn't work on version 6. You need to have 8 or better. So yeah, you're going to need, 10 is the current version, so go for broke and just get the new one. But yeah, it's not going to work on the old ones because I use newfangled JavaScript. Question. What does this blockchain do? It records transactions. Yeah, it's a ledger. That's what we're going to build. We're going to build a blockchain that records transactions just like Satoshi Nakamoto intended it for it to be. Satoshi Nakamoto, if you don't know, is the random, nobody knows who he is, that wrote the original blockchain paper. Okay, so those of you, I assume some of you have the code. I assume many of you would get it soon. Before we go into it, I just want to show the dependencies that we have. For those of you who are not familiar with Node.js, not to worry, it's a programming language. It's exactly like all other programming languages, as in that it's used to write programs. And that's really all that's important in this case, I think. Our dependencies. Now, there's a very small amount for those of you who have seen other Node.js projects, because I really didn't want to put in too many crazy things. So I'll just go from the top and explain what each of the dependencies does, so you can kind of see what we're building our project from. The first one is amqplib, which is a message queuing client, and we're going to be using a message queuing system to communicate with other nodes. Typically, that's not what you use. Typically, you would use a peer-to-peer protocol, but because that is ridiculously complicated, we're just going to cheat and use a message queuing system. It is a central point of failure, but it doesn't break the integrity of the blockchain to a large extent. Next one is big integer. This one isn't really needed. It's used to calculate the block target. The target is the number that the block's hash needs to be less than. And in order to calculate that value, we're going to have to work with really large numbers. And you use the library big integer to calculate that. The reason I say we don't really need that is because that number is actually stored in configuration. The next one is elliptic. That is for elliptic curve cryptography. That's a very fancy sounding, this is like real cryptography. It's elliptic curve cryptography. It's used for the asymmetric cryptography that Bitcoin uses and that we will be using. The way that it works is with asymmetric cryptography is you have a public key and a private key. And you can encrypt things with the public key, but you cannot decrypt it. And you can decrypt things with the private key, but you cannot encrypt it, and vice versa. Now, we're not going to be encrypting anything, but we're going to be signing. So in our case, you can sign something with a private key, but you will not be, you can sign something with a private key that can be verified with a public key. But if you have the public key and you have a signature, you can verify that the signature matches, but you cannot make a new signature. And so this algorithm is very nice because the private key can be almost any value. So you can just generate a random value as a private key and then calculate what the public key would be, and then you just go from there. So it's very easy to use from a consumer and developer perspective cryptography, and the library we use is elliptic. It's kind of built into Node, but we need to kind of, it's really much nicer to just work with a library. Then we use Lodash. Some of you may have heard of Lodash. It's kind of a functional programming library. We use it to kind of, in places where we really need to get nitty-gritty with collections and with arrays of values. We need to group things and so on. We've got LowDB, which is a very, very simple database. So simple that it just stores everything in a JSON file. And so basically, this is JSON as a database. It's really simple. It also uses Lodash, so you can interface it with with Lodash. And then you've got Object Hash, which is a library that allows us to hash an object. So we've got our JavaScript objects, and we want to hash them because that's the whole thing behind Bitcoin, is we need to hash our blocks, and we use Object Hash to do that. And that's all the dependencies that we have. These dependencies have some dependencies of their own, but not many. So that's pretty much it. That's very little. Now you can include more, and there usually will be more, but these are really all you need. And I think a big no-no in Node.js is everybody just installs dependencies for everything, like splitting strings and making things into uppercase. You don't need a library for that. You just write it. It's one function. Just write it. Anyway, so we have just our 6 dependencies, and if you're running locally, you can npm install, or if you are a real developer, you can say yarn install. I'm kidding. Yarn is better than npm in every way that I can tell. So just use yarn. If you don't know what yarn is, Google it later. Okay, and what I want to do now is kind of go through the code and show you the building blocks that we're going to use to build our blockchain application. I'm going to try and go quickly because we've got quite a lot to cover, and I want to come to the one that actually shows how the blockchain works. So I'm going to fly through these things. When you have any questions, please stop me. But the most important thing that I want you to know from going through these things is that the functions exist. The detail is you can check the details later. How they actually work might be very interesting, but the main thing we want to know now is that these tools exist. We know we have a spatula and a trowel, and they have different purposes. But we don't need to know how they're made. So we've got our file here, requiring some things. Yes, question? Sorry about that. The file name is up there. It's utils.js. So this is the utils file. We're going to start with the kind of really building blocky things, and we're going to, so as far as abstraction goes, we're going to start with really no abstraction. And then we're going to become more and more abstract. And as we go more abstract, high level, we're going to talk more about how things fit together and less about how things work. And that's kind of the reverse of what people usually does. So maybe it works, maybe it confuses living daylights out of everyone, but hopefully we'll all get there in the end. All right. So the first set of functions that we have in the utils file is encode and decode. And basically what that means is change binary data into a string and vice versa. The reason we do that is because first of all, we store it in a JSON file, and second of all, we want to display it on the screen. So whenever we work with binary data and code, we use it in binary. Whenever we print it to a screen or save it into a database, we encode it. And so we have our encode and our decode function. And basically, we use base64 as our encoding. Secret tip, anybody know what they use typically for Bitcoin? The answer is base58. Yes. It's like base64, only it doesn't have slashes and equals and stuff. It looks a bit nicer. At sacrifice for being a bit more verbose. And the next function is hash. This is our very important function that hashes a thing. Now it's got this thing called excluded props. And what that means is we get an object, and there are certain things that it won't include while hashing. The reason for that is, for example, you might have a hash value. Now, if you hash something with a hash value, the hash value will change. So you write a new hash value, and then you hash it again. You've got a different hash again. That doesn't make sense. So it's going to give you the ability to just exclude those. It's going to exclude things like hash and signature and one or two others that we'll get to. So this is basically what it does. It strips the props that we need to exclude. It removes some undefined keys, and then it removes them, and then it just calls that object hash function. It gives it an algorithm, SHA-256, is nice and secure, and it returns a buffer for us. So that's the one very important function. It gets used all over the place, and that's it. The next one goes hand in hand with it. It's called sign hash. This is a utility function that's the kind of the bones of how to make a digital signature, how to make a cryptographic signature. If you want to sign a block of data, you don't go through all the bytes of that data and sign it. You digest it first, so you end up with 32 bytes, and then you sign that. And so this function is for that purpose. It does the actual signature. It gets the private key. It signs, gives you a signature, and you pass the hash value to the signing function. It gives you the signature, and it returns the signature as a buffer using some stuff. Next one, we have a slightly more abstract sign function. This one takes an object. It takes an object and multiple keys. You can sign something with one or more keys. Can anybody know why you would want to do that? Why you'd want to sign something with more than one key? Anybody know?
Multi-signature, so like a wallet where you have multiple access to it.
Yes, that's very close. You said like a wallet where you have multiple accounts and you want access to them. Yes, but the place where you sign something with multiple keys is if a transaction has multiple from accounts. So a transaction needs to be signed by the private key of each account you're taking money out of. One transaction can take money out of multiple accounts, and it can put money into multiple accounts. And the numbers don't have to match, they just have to add up to 0. Or in the Bitcoin case, in our case, it needs to add up to the transaction charge. That's kind of how accounting works. But the way that we verify that a transaction was made by the one who owns that account is they have the private key for that account. And so we have the option of signing with one key or multiple keys. Now, we're not going to create any transaction with multiple keys, but it works. We know it works because there are unit tests. And so we'll see all that this does is it does some checks. It deletes, actually clones the object, that ... what equals what. That just strips the signature out. It deletes signature or signatures. And then it calls that hash, it calls the hash function from before, and then it calls that sign hash function. And just like I said, that's how it works. And then it returns, it will add a property called signatures or signature. Now, a thing that I want you to note that we'll be doing all over the place is, first thing is, I'm not using any classes. We don't need to use classes everywhere. There's, I think, only one class in this whole project. Everything is a function, and except for the index file, none of them use any state. And the other thing is, I really avoid mutating anything. So if you pass something into a function, it's not going to change it. That's why all over the place you'll see I'm cloning things. Over here I'm returning something new rather than changing something and creating a side effect. It's just kind of a thing that makes it a bit easier. So when you look at functions, you can keep yourself at ease. It's not going to change whatever you put into that function. It'll just kind of help you to think about it. Okay, so we've looked at sign. The next one is verify. This is the other side of the signature. It works exactly like we discussed previously. You take the hash of something, you take the signature of that thing, and a public key. And it will tell you if this signature is this hash signed by the private key that corresponds to that public key. So it basically tells you if you see a transaction that's been signed by a certain public key, this function would tell you if that's really so. Is this signature valid? That's basically it. And that's really it. I mean, it's just some validation. It just calls for the function of the library. Then we've got another function that's again a little bit less abstract, a little bit more abstract. It's just called verify. The previous one was called verify sig, where you pass it the signature. The next one is just called verify, and you just pass it an object. The reason we just pass it an object is because the signature sits inside the object pretty much every single time. So this one just pulls the signature or signatures out of the object. It hashes the object because you sign a hash, and then it verifies it. So those are the really important ones. We've got our sign, we've got our verify, we've got our hash. This is our cryptographic groundwork. Then we've got some other stuff. Generate key. It basically generates a key pair. We've got a function to get a public key from a private key. Yes, question? The idea is that is completely impossible. If it happens, then you've struck 1 in 2 to the power 256 almost impossibility. So that would be called a collision. It's akin to a hash collision. It's not quite 2 to the power of 256, but it's close enough. It's like 2 to the power. It might actually be quite a lot less, but it's so the likelihood is so small that it's unfeasible for you to go and find it. If you happen to do that, it would be a once in the history of the universe event. That's kind of the idea. And that's really is the security behind asymmetric encryption, is that this kind of thing is unfeasibly unlikely. But if you were to do that, you would have somebody else's private key. Get public key from private key. You only need the private key, and you can derive the public key from the private key. That's kind of a unique thing from this SEC P256K1, and I think most asymmetric cryptography, elliptic curve cryptography. Then we've got an abbreviate function, which just used to print stuff out. We've got calculate target. This is the function that calculates the target. Look at that big integer. That is 32 bits worth of Fs. That is the maximum hash value. Anyway, all this does is you give it a hash rate and a target time, and it will tell you what the target needs to be if you've got a certain hash rate and a certain target time that you need. So for example, Bitcoin is 10 minutes, so they keep recalculating the hash target to make sure that the block takes average of 10 minutes to create. We don't recalculate the block target because that's too complicated, but we need to calculate it at least once. So we have this function. Then we've got generate nonce. That generates some random bytes. We've got XOR buffers. Who knows what an exclusive OR is? Oh my goodness. Let me try again. Who knows what an exclusive OR is? Oh my goodness, that's better. At least lie. Like pretend that you know what an exclusive OR is. Okay, homework, go check what an exclusive OR is. This exclusive ORs, 2 32-byte buffers, or however size buffers. We need this when we calculate our little block problem. We use this, and this just does that operator, which is called apparently just up arrow, the exclusive OR operator, to two values in a buffer. That's all. Buffer less than. This is the thing that checks our value. It checks if the one buffer is less than the other one. If it is, you found the solution. If it's not, it will return false. It just loops through it and returns. And so those are our tools. Here's the list of them again. These are our tools. And the next things, we're going to take these things and we're going to stitch them together and we're going to use them to build stuff. And so the next file that I want us to look at, let's see. open up for me db.js. db.js is the file that kind of handles the database stuff for us. Like I said, the database is just a file. I'll quickly open the database. There's db.json here. And this is what it looks like by now. It's got a bunch of stuff. You can see most of it is just like these. This is what the keys look like. This is a hash value, that's a hash value, that's a public key, that's a hash value, that's a signature. They're all 32 bytes long, or roughly 32 bytes long. And that's what gets stored in the database. It's really boring. Let's see how tall our blockchain is by now. It's 215 blocks high. By the way, it's running in the background, so it works, I promise. So the reason I want to show the database is because that'll kind of show you what we need to store in order for the blockchain to work. And there's not a lot. So we'll go through this quickly. Now, what I want you to take away from this is it's not that complicated. Look, I know there's a lot of cryptography in parents, and there's a lot of places where it gets kind of hard. But at the essence, all the parts are quite simple. So we've got two functions to handle our keys, because we need to store that somewhere. So we've got get keys. Get keys returns the public keys, by the way. We won't ever return private keys, even though you can just open the file. We're just going to have some programmer integrity. We've got add key. You pass it the private key. That's what you call free documentation, by the way. It doesn't just say key, it says private key. This is what you call kind of misleading, because it doesn't return private keys, it returns public keys. And all that it does is it stores both. It stores the private key and the public key in the database. And then you've got a function getSigner. Instead of returning the private key, it returns for you a function that you can use to sign something, like a transaction or a block. That's kind of a way that you can give another part of your program something without having to pass the private key around in memory the whole time. Nice little functional programming thing. Functions returning functions. Nice. So you can see it uses some of the functions we've talked about already. Here we go. It does some stuff. You can have multiple keys, of course. That's what the three dots there means. You can pass multiple arguments. If you cannot find the private key, it's going to throw an exception. And let's see. You see, all it just calls is sign. And that sign function is the sign function we just saw in the other file. Most of the places I've imported the functions with the same names that were declared in other files. So you can just assume that when you see a function called sign, it's the same one referred to all over the place. And so that's what you use to sign things. The next things, we start with the blockchain. We've got a function that gets a block by hash, and we've got a function that gets the highest block. Those are important functions. We use getBlock by hash mostly to get a parent block, and we get the highest block is our important thing, important step. That one that gets the highest block, that we know which block we need to create. Okay, we've got store block. Store block stores the block in the database. If the name didn't give it away, it's got some law. It's got some basic checks, but not a lot. We've got store accounts. This is maybe something that we need to consider. So because the blockchain keeps building, a block contains transactions and stuff. Every time you create a block, the balances of the blockchain universe changes. But the balances are linked to that block, which means if a new blockchain gets created that makes this block irrelevant, these accounts don't matter anymore. So every block, along with every block, it stores a list of running balances. Now the way that something like Bitcoin does it is really clever, and you can maybe go look it up. But we do it the very simple and straightforward way, by for every block in the database, it stores an accompanying list of account balances, so that we can keep track of account balances and we can verify whether the transactions are real or valid. And so with every block, it stores, you have a method that can store the accounts. We've also got a method that gets the accounts. And that's it. That's all we need from a database. Something that's notably missing is the transaction pool that is kept in memory, and we'll look at that last. So that's the database. Any questions about the database? Yes, question. So question, where is it stored? It's stored just in a file. It's stored in a file that's configured in this file called configuration, and it will default to the file called db.json in the current directory. The keys, on the other hand, will be stored in a file called biob keys.json in your home directory. Yes, question?
What's the point in storing all the transactions, all the accounts in every block?
So it is not entirely necessary. Technically, you can prune the transactions and just recalculate them if you need to. I store them every time simply because that's easier and quicker to code and to work. But you don't have to store them. You can recalculate. You can. What I did initially was to just store the account balances for the newest block. But that means the logic for rebuilding the blockchain, if it comes in from the side or something, that logic became too complicated. So I decided just to store all of the account balances and make it simple. Okay, let us see what we've got next. Okay, next, let's look at something a bit more fun. The file blockchain.js. Now, blockchain.js contains the functions that we need to create the primitives of the blockchain. And what we'll talk about now is what goes into each of the objects. Who of you has any accounting experience? Any worked on ERP systems, done accounting in high school? Okay, there's some people with accounting experience, and apparently that is embarrassing. So the way that we're building a ledger, and the way that the ledger works is it's got transactions, and each transaction has multiple components, which we call splits. A split contains an account name and an amount. In our case, if an amount is negative, it's going to take money out of that account, or just value out of that account. If the number is positive, it's going to put numbers into that account. So we've got this function create split, which is never used, but let's just skip to create transaction. So create transaction takes a number of splits and a signer which will sign the transaction. And so typically you would imagine a transaction needs at least 2 splits, and it's actually got an incorrect validation. A transaction must have at least 2 splits, because there needs to be at least a transaction that money comes out of, and there needs to be a transaction which money goes into, otherwise the transaction is invalid. In accounting, we talk about double entry accounting, and what that means is the balance of every transaction. Double entry accounting means the balance of every book will be, if you sum all the balances of all the books, they will 0 at the end. But the principle is basically, if you take every transaction and you take all the amounts of negative splits and you take all the amounts of positive splits and you sum them, the result will be 0. Because the amount coming out of accounts and going into other accounts needs to match, right? And in Bitcoin or in our blockchain, the way that this is going to work exactly this way with one alteration, we need the amount to be slightly more. It needs to be slightly above 0 because of the transaction charge. Yes?
In terms of these, what happens if I'm running 2 transactions the same time, 2 different output accounts? Say I've got like 10 units in my account, and I try to send both of those to 2 different accounts. How does it differentiate it? How does it pick which transaction is valid and not valid?
So in that case, it will reject the transaction as a whole. Because as we'll see a bit later when we look at the validation, what it does is it actually checks the splits in the transaction, and it checks that they sum adequately. If it sees that you try and create a transaction that takes 10, yes, what shall we call it? 10 numbers, 10 rabbit coins, out of, if it takes 10 out of the one account and it tries to put 10 into 2 different accounts, what you've got is you've got less money coming out than is coming in. So it's not going to, so remember, this is one transaction. This is not multiple transactions. If you try and have multiple transactions, it will throw it out because it will say, it will throw the second transaction out because it will be invalid. Yes, Derek?
So the question was, you're making 2 transactions coming from the same source account for the same spend.
Yes.
2 transactions doing the exact same thing.
Yeah. So if it's 2 transactions doing the exact same thing, it will get thrown out when you try and validate. So, the second one will fail. Yes. So maybe that answers your question better. It's going to go through the accounts, and the first account, it basically goes to the transactions, and if it finds a transaction that results in a negative account balance, it's going to throw that transaction out. Yeah, so this function creates a transaction. A transaction has, let's see, so a transaction has only this. It has splits and a signature. It also has a hash. Pretty much everything has a hash, except splits. They don't have a hash. So really only transactions and blocks have a hash. So a transaction, but there's one other thing that a transaction has. It has a nonce. So a nonce, it generates it here. The reason a transaction has a nonce is so that you can differentiate between multiple transactions. So let's say somebody puts a transaction on the blockchain. It gets, let's say a block gets created and your transaction wasn't in that block. And here you sit with the transaction in your pool, and there's a transaction in the previous block which is the same amount to the same account from the same account. It's the exact same transaction anyway. How do you differentiate it from another transaction? Well, the hash needs to be different. How can the hash be different if the signer is the same, if the splits are the same? Well, there has to be something extra to make it different. So you put in a nonce, which will make sure that every transaction created by this function will be unique in every way. This also means, now this is not a requirement for our blockchain, but it's a legitimate requirement for our blockchain, is that every single transaction have a unique hash. That would mean that double spend would just be a little bit more difficult to do. So you won't be able to, for example, say, I'm a recipient for this money. I see the guy put the transaction in. Let me just broadcast that same transaction a couple more times to make sure it comes again. So no, you can't do it because the transaction will have to have a new hash. All right, so that creates a transaction. That's the one, that's kind of, we have 2 kind of entities that we're working with. Transaction, we kind of covered splits. We've got transaction, which consists of multiple splits, and then we've got a block, which consists of multiple transactions. And here is a block. A block has this. It has transactions, it has a height, it has a parent, and it has an author. Now this does not take a signer as the previous one does, because we might need to recreate this block multiple times. And lastly, we need to create the block, we need to hash it, and then we need to find the solution to the problem before we can finalize and sign it and publish it to the block. And so here we see what it does. It calculates the hash, so it has a hash. So like I mentioned before, in our case, the block hash doesn't change when we try and find the problem. We just change something else called a complement. We try and find the complement that goes with the block hash. It's a bit easier than having to rehash the block all the time. We have really slow hashing, like really slow. So, yes?
Okay, so essentially with this model, you pick, when you try to create a block, you pick a fixed set of transactions and then try to create the next block from those transactions no matter what. As opposed to you technically have the option of every time you try to generate a valid hash from a block, just pick a different set of transactions.
You could do that.
But there's no obvious advantage to just generating a hash, I'm just saying, so that is the frustrating misconception that we apply.
Well, we create blocks with, you will see that when the process runs, every time anything changes, you create a new block. This block is not signed. It means nothing. The block is only valuable once the correct complement has been found and after it is signed by the author. Then it's valid. So this block gets created. It's kind of an unfinished block, which is why the next method is called, well, we have a recreate block method. It's just a utility method that recreates a block with the same set of transactions and same author and everything. But we have finalize block. We change the block, the complement, and the signer. And this finalizes the block so that we can transmit it to the network. But first of all, what I just want you to notice is this is all that goes into the block. It's got a complement, it's got a list of transactions, it's got its height, it's got the parent's hash, this is a hash for the parent, it's got the author's public key, and that's it. It's also got what will also be stored in here is the hash, but that's not important. So, question, yes?
Validate flow.
Oh, so in this method and this method, just to make double sure that we don't accidentally put an invalid block on the network, we find the solution to a block only to find that due to human error it's invalid. We validate the block and throw. Validate throw basically calls this function and throws an exception if the block is invalid. So the idea is that if you call this with transactions, height, parent, and author, all these things are, you've already checked that all these things are valid. And if it's not valid, this thing is going to throw an exception. So this just makes sure that the block that you created is valid. So this function won't ever return an invalid block, and this function won't ever return an invalid transaction. Okay. We've got recreate block, finalize block, and lastly we've got hash block. Hash block is just calls the hash function. It's a bit special because what it does is it adds the hash property to the block, and you can see again it's returning a new object with all the properties from block and the new hash property. And the hash property is special because it needs to hash but exclude the signature, the hash, and the complement. This is the reason we're excluding those is because the complement is kind of in our case, like I said, we're not changing the hash as we try and find the solution to the problem. We're just changing the complement around. All right. And so that is it for our blockchain primitives. Let's see what's next. So next I want us to look at the next crucial thing. Like you see here, in order to finalize a block, we need that complement. That complement is the solution to the proof of work puzzle. So how does the proof of work puzzle work? So we've got this function, this file called solver and solver.worker. So this file is a bit needlessly complex because it involves some inter-process communication. The way that this works is a bit funny because Node.js is single-threaded. So we cannot calculate the block solution in the background and merrily go on the way we want. I mean, there are some ways you can kind of get it to work that way, but I thought the more clean way to do it is to make it run in a different process. So the way that it works is it's got a worker that is a separate node process that runs in the background, and you communicate with it by sending things to the standard input. And what that means, it's the same thing as doing this, solver.worker.js, and I run it, and you'll see waiting for input. And what it's waiting for is a hash value, and it says it's looking for JSON actually. So it's going to take an input message, and it's waiting for the problem. If you give it the problem, it's going to start solving. And I'll quickly show you how that works. So it's got start worker. This basically starts the worker. So what it does is when you call this function called new problem, you give it the hash and the target. The target is fixed. That's in configuration. But you got the hash. And what it's going to do is it's going to find a complement that goes with this hash that will put it underneath the target. That's kind of what it does. In very simple terms. And so I'm quickly go through this and you can see how it works. It's got some stuff. It's got some stuff that calculates the hash rate in case you care. It like logs stuff the whole time. And so basically this is what it does. It goes for a certain number of iterations and then it prints a message. That's all we've got there. And so as you expect, we've got a for loop. All that it does is it starts with iterations, it'll go down to 0, and it increases a little counter for us, which has nothing to do with the other one. And this is what it does. It gets random bytes for the complement. Bitcoin would just increase it by 1. I just chose random because that feels better. It does this XOR buffer thing with a hash and the complement, and then it hashes it. Digest. And then if it's less than the target, there we go. Found solution after so many million hashes. And then it writes it back out. And that's all it does. It takes the problem in, it loops over and over, and then when it finds this random value that makes this function return true, then that's it. And that's all that this function does. Now I need to make sure you guys understand this. I mean, it's not really that important to understand how all this XORing works. But basically the idea is this function, it finds the solution to the problem. And the solution is that value called complement. The problem is making sure that the exclusive OR of the hash and the complement is less than, and the hash of that is less than the target. All right. By the way, there's a vulnerability in that. I thought of it today. There's a huge vulnerability, which goes to show why you shouldn't be tweaking with these kinds of cryptographic stuff. If any of you can figure out what the vulnerability is with my way of doing it, please come and tell me. I want to see if anybody can figure it out. It's not a huge vulnerability, but it is a vulnerability nonetheless. It'll allow you to find a block. It's very unlikely, but it can allow you to do something which you shouldn't be able to do, or you aren't able to do in the Bitcoin blockchain. Anyway, so that's how the solver works. You call a method called solve, or find problem. And just to go back to the solver function, it returns a promise. And in JavaScript world, that means it's asynchronous. You see, you've got the function solve, which is the more abstract version. It's async, which means it's going to return something that's going to resolve later. It's not going to resolve immediately. And that's really all it returns. It's got a bunch of other functions that we never ended up using. And then, so that's the solve function. And now I want to start looking at some of the questions that have been asked, because I can see many of your questions are, but how can I JIPO this? And the answer is, that's actually the thing that most people skip over in their build your own blockchain things. So I have gone to painstaking effort to make sure that that doesn't happen. So I've got this file called validation, which I think is the largest file, 380 lines, and it validates everything. It checks if things are valid, base 64. It checks if things are valid, public keys. It checks if the hashes are valid hashes, which is, the hash is random, so it just checks that it's a SHA-256 hash. It checks if something is a valid private key. It checks that splits are valid. For example, you can see here an account is required, an amount is required. Things like the amount must be greater than 1e minus 15. The account must be a valid public key. The split contained extra unsupported properties. That's kind of a thing I wanted to avoid, is that you can add like an infinite number of properties in there. And that's another thing we didn't talk about, is blockchain forking, and I'm just going to not talk about that because you can research that on your own. Then we've got validate transaction, and this is kind of where the things start getting interesting. You can see it takes all of these properties out of the transaction and is going to validate each of them. You see here, there I made a mistake. A transaction must contain at least one split. No, it must contain two. A transaction must be signed. A transaction contained extra properties. Then it starts doing more detailed things, like it's checking if there are any problems with any of the splits. There were problems with splits. And then it tells you what problems were there with the splits. Then it starts checking, it divides the splits up into splits that are below 0 and above 0. And it checks the totals, the total from and the total to. And it makes sure that the one is greater than the other. Then it checks that the from amount is less than the to amount. It cannot be, you cannot have more money going into accounts than it's coming out of accounts, because that's not supposed to be possible. Then it makes sure that there's a transaction charge. The debit and credit totals were equal. If they're equal, unlike in real world accounting, this throws out the transaction if there's no charge. Then it makes sure that very important, that the transaction itself is signed with every split that takes money out of an account. So it goes all the from accounts and it verifies that they're signed. The transaction was not signed with by each from account's private key. Grammar. So that's validate transaction. And you may think to yourself, you need to do more than this, and we do. Just hold on. Then we've got validate block, which validates a block. Now, let's look at the validations we got here. It checks that there's transactions array. It checks that there's a complement. It goes some more checks. These are kind of just basic checks. Does it have an author? Does it have a parent? No parent was specified, but the height was not 0. You cannot create a block in the middle of the air. It needs to have a parent. It then goes ahead and checks every single transaction. If there's any problems, it will reject the block. It checks if there are extra properties. Now, these were just cursory checks. Now, the thing about this one that says validate block is this can validate a block even before it's been signed. So this is kind of just basic validations. We'll go down. I'm going to skip down a bit and come back up. Now I've got validate transactions deep and validate block deep. These are the more thorough validations that check if a list of transactions or a block is eligible for being included in the blockchain. Validate transactions deep takes a list of transactions and accounts. These accounts should be the account balances of the parent block. And it checks every single transaction and checks that if it can be applied with the current list of balances. It basically goes and it calls this function. Actually, it calls get invalid transactions internal. And what this does is it basically creates a list of accounts, and then it starts going through all the transactions, and it starts building its own record of accounts. And if there are any negative account balances, it knows that the transaction was invalid. And then it's going to make a list of those transactions and report on them. A reason we split it up is because we need to have a way of removing invalid transactions without removing all the transactions together. Question. By the way, if I don't notice that you've got your hand raised, just throw me with something.
All accounts from the beginning of time.
Good question. Question was, does this include all the accounts from the beginning of time? These accounts would be the account balances for the parent block. So typically that would be all the accounts from the beginning of time. But the way that it works is it will accept any block into the chain, even if it's not at the very top. In which case, if it's like a new block that's a few levels down, it's going to check all the accounts at that point in time. So basically, it will look at all the accounts since the beginning of time up till the parent block, and then look at all the transactions that you're trying to add in the new block, and trying to make sure that they make sense. Does that make sense? The exclude invalid transactions. This is used for our transaction pool. If we have a pool of transactions and a new block gets added, we need to remove all the transactions that are suddenly invalid because of the new block. So if somebody wants to spend money, a new block gets added, and he spends some money elsewhere, and now he has no money, we need to take out that transaction that is now invalid. And this function does that. It makes a list of the problematic transactions and removes them. Returns a new array without those transactions in them. And this validate transactions deep, again, it just does the same thing. It gives you a list of all the transactions that are invalid. That's for rejecting an entire block, because a block cannot have invalid transactions. Because remember, when you create a block, the parent block cannot change. So if your transactions are invalid, that means that block is fraudulent and it shouldn't be included. So the whole block gets rejected if there's one invalid transaction. Then this validate block deep does all the checks. It checks if the block solution is under the target. It checks that the block parent exists and that the height matches up. It checks that the block signature is valid, that the block is signed by the author, and it checks for any invalid transactions. That is the validation. So these validations get applied every time a new block is received, whether it's one we made or one somebody else made. We check these validations and we check. Now these validations are very important because without them, the blockchain doesn't have integrity. Validation of the blocks in the blockchain really is a core principle of building a blockchain. This is what makes something like Ethereum such a complex project, because this basically allows the various contracts to set their own criteria on what is be considered a valid change to a contract or not. And the underlying Ethereum system needs to do the same. And so this is the principle. Remember, anyone can create a new block. Now there's an incentive to create an invalid block because you get some money, but there is a very, very large incentive to create an invalid block. Because like we saw a couple of weeks ago, somebody created invalid Bitcoin gold blocks and made many, many millions of dollars of money because they made invalid blocks. Now the reason I kind of wonder about how that actually worked, because in a blockchain it shouldn't be possible to do a double spend like they did with Bitcoin Gold. Because anybody can check that there's invalid transactions. Now, what most likely happened in that case is somebody created money, spent money, and then those blocks get thrown away. But the idea is that if anybody creates an invalid block, the block gets rejected. So if somebody tries to spend the same money twice, the block that tries to do the double spend will get rejected because you can check. Yes, question?
Like a observation in the second there. Normally with the validation, when you have a successful block and you publish it to the network, there needs to be consensus in the network saying that they accept your block, and there needs to be a percentage of the network that your block is valid. So the problem comes in is you own and you go to the network and your network is corrupt. Then you can accept these invalid blocks and say they're valid, and then they can force into the chain.
Yes, now I think that's where the misconception lies, because it doesn't matter what percentage of the network accepts the block as valid. It matters what you accept as valid. So if I connect to the network and I play by a certain rules, if somebody somehow managed to get 90% of the network to accept transactions with invalid signatures, and I don't, I will ignore all those new blocks because they're invalid. And I will look at the blockchain for the last point that I consider it to be valid. Yes?
But now you just forked the chain.
Yes, exactly.
And now your chain is invalid because 90% has consensus on the previous chain.
No. See, you use the right word. The block is forked. My block is not invalid. My block is now a different blockchain from the other blockchain. It's valid for me.
For everyone else, and that's where the store of value is, it's invalid, so you can't now use that to swipe on the original chain.
And that's, I think, where the thing is. The decision of where value lies is not by the miners. It's by the consumers of the blockchain. It's by the exchanges. The people who decide if Bitcoin is worth so many dollars, those people aren't miners. So if you say I control 90% of the network, what you mean is I control 90% of the miners. And that doesn't mean that I get to decide what blockchain is worth, what Bitcoin is worth. So I can control 90% of the network and change all the rules, but then somebody else, like an exchange, for example, who changes dollars into bitcoins and vice versa, they can then say, but I don't care what they say, because maybe what they say is complete nonsense, because that's probably what you can think of as like somebody managed to use quantum computer and they changed all the rules and now I can use unsigned transactions and anything goes and everything is programmatic and now everybody steals money. But no, the exchange can say, I work by my set of rules. I'm going to accept blocks that, according to the rules that I agreed on, and not 90% of the network can change my mind about that. That's why that's why Bitcoin can fork, because it's not about majority. It's about who accepts the rules. Yes.
How long does it take for the difficulty to update in the case of a fork? So like say 50-50 it splits, I'll need to maintain a hash power in order to actually find these blocks. So how long does it take until that stability decreases to where that is still the fork?
That's a very good question. And I've wondered about that myself. I'm not sure exactly what it does. It could be that a part of the fork is to change the hash rate. I don't know, because Bitcoin did fork, I don't know what they did. I don't know the exact details. But the answer is, if the hash rate were to be diced by, let's say 90% of the hash rate was lost, it will mean that the next block will take 10 times as long to create. I'm not exactly sure about the technical details of when the hash rate will be updated, but it's going to be a while.
But isn't that like a programmatic way of trying to disincentivize forking? Because you need to then maintain until the next difficulty updates. So
I think it will disincentivize kind of doing a subterfugal fork, like trying to do a sneaky fork. Because like the Bitcoin fork into Bitcoin Cash, that was planned. And Ethereum updates its virtual machine like once every now and again, and that also forks the Ethereum blockchain. And so any nodes that don't update their software, they will continue to work with the old rules, and the idea is that they should upgrade. But they call that a fork because the new blocks aren't compatible with they'll be considered invalid by old software. And that's kind of the idea, and I think this is one of the... Yes, 7:49. You got 10 minutes. No, man. Okay, we're skipping to the end. TLDR, there are tons of validations. I'm grateful for all the questions. I hope this helps to understand things. Okay, let's skip to the end. Excuse me, I'm going to sit down. My back hurts. I've been lying in bed for 2 days. So we'll open the last file called index. No, oh my goodness. Don't jinx it. Okay, open the index file. The index file is very interesting. It's different from all the other files because it's the file I wrote today after 2 days being sick, and so it's considerably worse code. But it's different also because it includes all of the other files we discussed so far. It's going to use all those tools and blocks. And here we've got, there's a pool of transactions, really boring, it's just an array. You've got the current block being mined, and we've got our messaging client. We skipped over that one, but TLDR messaging client uses to communicate to other nodes. Okay, so let's skip to the end of the file because I don't know why that does. Every program I've ever worked on, the main file is at the end. And I think that's because in C, it needs to be at the end. But everybody does it, and so did I. It's at the end. Why is it at the end? Anyway, if I didn't put it at the end, it would confuse everybody else. That's why. Anyway, it's at the end. So this is what we do. Main, we come in. We generate keys if needed because it might be a first run. We've got the messaging client that connects to the broker. So it starts using configuration. It uses this. This is my identity. If we look control shift space, it's got an identity. Identity is my public key. That's just the way that other nodes can communicate to me directly if they wanted to. We connect. Then we just hook up some event handlers. These are the possible messages we can receive. This is the message for receiving a block, for receiving a transaction, for receiving a response for the highest block. We'll see that in a second. For a chain request, it's possible to ask another node to send you the entire blockchain. If any of you have run the project yet, you will have seen that it downloaded the entire blockchain. And then we've got the so we've got a request for the highest node, we've got a response for the highest node. That's it. Then very first, it does a broadcast. When it starts up, it does a broadcast and does a request highest. And what that does, it broadcasts to all the other nodes to tell me what their highest block is. And then what it's going to do when it gets that is it's going to check, is that highest block higher than my block? And if it is, this is all a lot of stuff. It's got some debouncing because that's necessary. It might receive 100 responses or whatever. So it needs to check the highest one. And what it does is it sends that node a chain request. So it basically checks which node has the highest block height, and it tells that node, give me your entire blockchain. But that's getting ahead of ourselves. The thing it does at the very start is it starts mining. Seriously, control click. There we go. And this is the mining procedure. This is the thing it's going to do over and over again until it finds a block. And it does this. Now note that it's async. It means that it's going to stop in the middle and maybe only come back later. So keep note of that. So it's got block, reinitialize block. Okay, I'm just going to stand up because this is not working. Apparently, I'm meant to stand. Okay, so we've got reinitialize block. That recreates the block. New hash, new transactions. If nothing changed, it will just be the same. Then what it does is it gets the hash, which is the problem it's going to try and solve, and then it does this. Await solver.solve, hash to solve, and the target. And it's going to get the complement. And that's what it does. And this is going to wait until it finds it. Now, while it's waiting for that to happen, a number of things can happen. And that's why in this diagram, you've got basically two things that can happen. A new transaction can come in or a new block can come in. Either of those things happen, things have to change. So let's see what happens when both of those happen. First one is, let's say a transaction, receive transaction. So what it does when it receives a transaction, the first thing it checks is, do I already have the transaction? If I don't, it adds it to the pool. Then it does a whole bunch of checks. If there are any errors, they say, there was a problem with the received transaction. It logs it to the console and it ignores it. Otherwise, we've got a new pool of transactions. And when we've got a new pool of transactions, it calls the mine method again. Now, this is an interesting thing about the way that the solver program works, is it will update the problem. It will just continue mining with a new hash value. So there might be multiple of these mine things. This mine function might be called while the other one is still going. But it doesn't matter because in the mine function, as soon as it gets the complement, it's going to check if it matches the hash that it was called with. See that technical, that's a capture. It's captured that value, and it will check if it matches. Check that the solution is still relevant to what it was when this specific function was called. And if only the one where it was valid will be good. Okay, but so that's the one thing that can happen, a new transaction. The other one is a new block can get received. For a new block, it does kind of the thing you would expect. It checks if we already have the block. If we don't, it prints a console message. It gets the parent block accounts, and then it calls that validate block deep function. So this checks if everything about the block is valid. If it is, it does a whole bunch of things. It calculates new accounts and stores them with a block. It stores the block, and then it checks if it's the highest block. If this new block that we received is now the highest block, it is the new authoritative blockchain. And then what we do is we have to recalculate the transactions because they might not be valid anymore, because our pool of transactions is always based on the highest block in the chain. And also, those transactions are very likely inside the block that we just received, if it's the highest block. And so what it does is this excludes all the transactions that is in our pool, that is in that block, and this next one excludes any transactions that are now invalid because of the block we received. And then it does it again. It starts mining. So those are the two ways the mining process can be interrupted. And do me a favor, those of you who have got the project on your computer, fire it up and have it run and have it mine. And I'll log in and I can see. You can see my password. So these are all the queues. These are all quite a number of you that are connected. There we go. That's more than I expected. Congratulations. This bottom one. You are running old version of the software. And I have to manually delete that. So if you downloaded this earlier today, please pull again and restart. Well, I'll do this later. Your thing is going to crash. And so what happens when it finds a block? When you find the solution to a block, a number of cool things happen because you now found what is supposed to be a very rare solution. It signs the block and it finalizes it. So it finalizes it by giving it the new complement, which is the solution, the signer, and then it calls the very same function that is called when a new block is received from the network. And then it broadcasts the block. And that's it. So let's see it in action. So I'm going to stop the program. Zoom in. Oh, is this going to work? 900% zoom. No. My zoom in function is obviously broken. Oh, make it go away. Oh, no. Why is it doing this? Here we go. Okay, let's see. I'm going to make the font bigger. 36. Yes. I'm going to run it. So, here we see, connecting to the broker. Yes. Mining for block hash. There we go. Ooh, it's receiving blocks. We've got a very high hash rate now. It's receiving blocks. Now, what you're seeing is what is happening every time it's receiving a block from somewhere else. You can see the received block, and that's the hash, kind of just a piece of the hash. That's the new highest block, mining for block blah, sending highest block to block. Now this, what you see here is kind of asking for its own highest block. It kind of is a feedback loop, but it doesn't matter. But basically all you're seeing is whenever a new block is found by one of y'all, it gets broadcast to all the other nodes, and you can see here what happens when it receives it. It kind of updates. Now, there are no transactions in these blocks. Nevertheless, there is money because, and that's a file we actually skipped. there's a file that does the accounting for the transaction. It's accounting.js. You can look at it later. But if you look at the bottom of the file, you'll see this is all these are all the account balances. Now, these account balances, except for my testing here and there, are exclusively for finding blocks. The block reward is 1 for finding a block. And you can see it's updating the whole time as people are finding new blocks. Every time they find a block, a number gets added for them as the new accounts get added. We've got 11,000 lines. Oh, we're going to push this low DB to its limits. Okay, so I know our time is up, but if you cannot go yet, I'm quickly going to do a transaction. So I can close my nodes since there are so many of you. I had to keep it running because if no nodes are running, there's nowhere to find the blockchain, and it kind of makes a mess. Because right now, the only place where it checks for a new blockchain is at the start. So it's possible for 2 nodes to mine indefinitely. So I've got this little file called transaction publisher. Now what it does is it tells you your accounts. You can have multiple accounts. You can check the code if you want to see how to do that. It tells you your balance. It gets this from the blockchain, by the way. And what key do you want to use? It's going to use the first one by default. How much do you want to transfer? Let's say 10. And what's the destination account? Now the default is random. It's got a list of all the accounts that exist already. It can be anything actually, because a public key doesn't need to exist anywhere for you to be sent it to. If you send it to a random number of bytes, you have destroyed some bitcoins effectively, or some rabbit coins. So I'm just going to say random. It's picked that one. What is the transaction charge? The default is just 0.1. I'm going to be that fine. And it's going to go. That creates that transaction, and it's been sent. There we go. So that transaction is now just been sent to the network. And we'll go now and see if it worked. So here you can see it's from account what's it, A6UUI or whatever, and it's to account AKFLX. So let's quickly check our file, and I'm going to maybe open it in Notepad or just copy it to Notepad++ because that one keeps updating. I'm going to paste it, and we're going to look for that 10. Or I think that will do. There we go. No. 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 Oh boy, this is not going to work. Okay, I'm going to look for it the hard way. Okay. What will be funny is if you don't find it. And there is some kind of bug and the transaction is not included. That will be annoying. Oh my goodness, it looks like it's not here. Oh, but I stopped the node, of course, so it's not being updated. So this is what happens if a node gets started and there's another blockchain. Look, it's going to send, whoop, there it got all the blocks that were created in between. So what happened now, by the way, just to recap, is I'd stopped my node, so my transactions weren't being updated. And when I started it again, it asked one of the nodes for all of the blocks in the chain, because it's not complicated. It just asks for everything. And what you saw there is it getting all the transactions. So let's try again. I'm going to do this. And let's see if we can find that transaction. And if we can't, sorry, but I think it's there. So what it does is it asks all the nodes for the highest block, for the height of the highest block, and then it picks one and asks that one. Let's see. Here we go. There's our transaction. The amount is conspicuously incorrect. But that's because that's not my transaction. That's somebody else's transaction. There's my transaction. You all are clever. You're creating your own transactions. Okay, so there's my transaction. So there we go. We have a working blockchain. These transactions are recorded on our blockchain, and you could probably change this, but I would say with 10 nodes, it's probably going to take several minutes to override these blocks. And this is on a very, very easy block solution. And so this is, I think, we can say, a legitimately working blockchain. Congratulations. We have our own blockchain. All right.
So I think we've come to the end of the evening. Those of you who need to run off, I'd recommend Ubering to Rosebank rather than Park. Jerome, I'm literally messaging you that to you, so please go to Rosebank. Any questions? I'll bring the mic to you.
Will this stay online after the Rabbiteer session?
You mean the blockchain? I can try and make that happen. Yeah. I'll try and put the blockchain application on the server. It only runs single-threaded, so it'll kill only one of your server CPUs. We'll try and figure that out. Get it on like some kind of cheap free server. Otherwise, the code is on GitHub. It's available. Check it out. See if you can improve it. It is a fully working blockchain. It is not a secure blockchain. There are tons of vulnerabilities. Most of them, the ones that I know about, are denial of service vulnerabilities. There are probably many that I don't know about. So security is very important for blockchain, so do not ascribe any real value to this stuff.
Cool. So I'm going to jump in there. Whoever's here, I want to do like a photo. We haven't done this before, but I think we need to do it. So whoever's feeling excited, like throw your hands in the air on the count of 3. I'll move as far back as possible. Okay. 1, 2, 3. Rabbiteers! And I've got to get the other side of the room because that's a shitty phone. 1, 2, 3. Rabbiteers! Woo! Thanks, guys. Yeah, carry on. Had to happen, sorry.
All right. This has all been recorded. We'll have it online at some point. The code is not going anywhere. It's on GitHub. It's open source. And I am also on GitHub, on Slack, on LinkedIn, on Twitter, whatever.
What is your Twitter?
Questions at Cillié Malan.
Oh. I think you exhausted people, Cillié. Well, thank you very much to everyone coming to Rabbiteers. I hope you enjoyed yourself. Thank you, Cillié, for powering through when this morning we thought you were dying. So I'm glad you're not. And we'll see you guys next time.